Hey, what's up, Chem peeps? Today we're going to talk about some Unit 7 Day 2 practice and hopefully get you squared away with some important concepts. The first of which is here on this first question 1. It's asking you to think about the relationships that exist in this equation related by Kw, and that the product of the hydronium and hydroxide concentration is always equal to 1 times 10 to the minus 14 as long as you're at 25 degrees Celsius. If you take a look at the simulation that we used together in class, right, it's just kind of a great visual to see what's going on here. We're starting with pure water, right, where each of those concentrations are the same value. So each of them are 1 times 10 to the minus 7, which when multiplied together will equal 1 times 10 to the minus 14. However, the goal here is to recognize if you are increasing the concentration of hydronium. So if you're increasing the concentration of hydronium, the hydroxide ion concentration is going to decrease accordingly, or vice versa. If you increase hydroxide, hydronium is going to go down, so that the product of the two concentrations will always equal 1 times 10 to the minus 14. And that's where we are here in this question, right? Recognizing that the hydronium ion concentration has increased from 1 times 10 to the minus 7 up to 1 times 10 to the minus 4. And in order to keep Kw constant at constant temperature, this concentration must go down. And so as you look at it in the simulation, I'm going to drop this all the way up here to 1 times 10 to the minus 4, which means that the hydroxide has gone down to 1 times 10 to the minus 10, right? But how do we do that without a calculator or without a simulation? It's remembering that this stays the same, the Kw value. And so essentially, you're just dividing each side by the hydronium ion concentration to solve for hydroxide. So when I divide each side by 1 times 10 to the minus 4, right, it's going to drop it out on that side. And when I divide two numbers that are in scientific notation, 1 divided by 1 is 1. And then I subtract my exponent. So negative 14 minus negative 4 is going to be 10 to the minus 10. That is my hydroxide ion concentration. Boom. Now, it's important to remember that as you are working with these different concentrations, whenever you have more hydronium than hydroxide, it's going to be acidic. And if you have more hydroxide than hydronium, it's going to be basic. So keep that in mind as you work through question number 1. All right, next question I want to take a look at here is this one, right? You're given a list of weak acids and their corresponding Ka values, and you're asked to identify which is the strongest base, conjugate base, right? And so this one is really asking to think about the equation or the relationship that exists between Kw, Ka, and Kb. And it's important to recognize that at 25 degrees Celsius, the product of the Ka and the Kb will always be 1 times 10 to the minus 14. Now, you don't have to do this math, especially I don't have a calculator, right? But just to kind of visually see what happens, right? I'm going to pretend this is 1 times 10 to the minus 2. And let's just say this is 1 times 10 to the minus 5, right? If I know the Ka and I know that's 1 times 10 to the minus 2, right? Then as I divide each side by 1 times 10 to the minus 2, my Kb is going to be equal to 1 times 10 to the minus 12, right? Just focus on the exponents there, which is going to be a pretty small Kb, indicating a fairly weak base. I mean, they're all weak, but pretty weak, 10 to the minus 12. I do the same thing here, right? Again, I'm just estimating the Ka value, but this relationship is still the same, right? So 1 times 10 to the minus 5 is now my Ka, and this is still 1 times 10 to the minus 14. So when I solve for Kb, again, I divide each side by Ka, I'm going to get 1 times 10 to the minus 9 as the value of my Kb, which is still indicating a weak base. But what we're doing is we're comparing these values to one another. And we're not trying to say that the base is strong. We're trying to identify which is the strongest, right? And so you're looking for the one that's going to have the largest Kb value. So do I have to do all this math and make all this estimations? No, right? all you have to do is recognize how this math works. And if you do, then you recognize that whatever Ka is the smallest, the corresponding Kb will be the largest, right? So you're just going to scan your list, being very careful because you've got these things listed in not in order, and right, you're working with negative exponents. So remember, 10 to the negative 5 is actually the smallest value here, and it's going to correspond to the largest Kb value. All right, and then last one for today, you're working with an equilibrium reaction, and you're told the value of the equilibrium constant for the reaction, and you are trying to figure out, which answer shows the bases and their relative strengths, right? So first we identify what the bases are, right? So we're going to do a quick pairing here. This is an acid. This is its conjugate base, right? They differ by one hydrogen ion. This is a base. This is its conjugate acid. So we're trying to, kind of decide, is H2O the stronger base or is F minus the stronger base? And to answer that, right, you're really going to be thinking about how we define strength. So here I have just a general equation, let's say reactants in equilibrium with your products, right? And in this case, K is less than 1, right? Our K value is something less than 1. And what that means is there's more reactants than products. And what's somewhat confusing here is recognizing that the thing that there is more of is the weaker thing, right? As you think about what we mean by strength, right? The stronger things, they don't stay together, right? They're going to ionize and go the other way. So imagine just like this muscle arms are like pushing on the equilibrium. Because they're strong, it's going to go more this way, right? Make more reactants. The weaker things, right? Here's my little weakling arm pushing back the other way, not going to be able to push as successfully to make as much product. So in a case where the K value is less than 1, right, you're actually going to have more reactant than product. And what that means is that the products are stronger. Conversely, although not part of this question, right? What if, alternatively, we have a situation where K is greater than 1, right? In a situation like that, it's just kind of reversed, right? We've got the strong things on the reactant side and the weak things on the product side. Remember, when K is greater than 1, that means that you have more products than reactants. And so what we're saying here is that the reactant side is the strong side because now they're pushing more, making more product, than the weak side is able to kind of like, push back the other way. So as you think about this question, it's kind of a twofer, right? You have to think about identifying the acid-base conjugate pairs and then recognize, what the value of K means. When it's less than 1, there's more reactant than product. When it's greater than 1, there's more product than reactant. And then whatever thing there is more of, right, is actually the side that the weaker things are on. So this is the weaker, not part of this question, but weaker acid and weaker base. And this is the stronger acid and base. Okay, hope that helps.